Hi everyone. All of us know that there are many techniques for advanced material characterization. Some of them are XPS, Rutherford backscattering, and it keeps going on. I'm going to talk about atomic force microscopy, which is commonly known as AFM. First, let's see how it's made. The atomic force microscope has a major component which is called the cantilever. The cantilever is a horizontal rod pivoted at a joint which can oscillate back and forth. There is a tip connected to the cantilever and which is responsible to move over the sample. A laser which gives out an incident beam on top of the surface of the cantilever, and a detector which detects the reflected beam from the surface. The main principle behind AFM is the tip is brought very close to the sample of to the surface of the sample, and there are strong van der Waals force of attraction at a range of say 10 nanometers, and when the tip is brought so close, the attractive force pulls this tip towards the sample. But if it goes even more closer, there's a strong force of repulsion. This helps to keep an optimum distance from the sample, and the tip is able to move over the sample. In the detection method, as we have seen, there's a laser beam, and the incident laser goes onto the flat surface of the sample. Sorry, not the sample, but the cantilever. And as we have noticed, when there's a surface and when there's an incident ray, as the surface keeps moving, the reflected ray also keeps varying, right? The same logic applies here. As the cantilever has to move depending on the surface, there are variations in the reflected beam, and this deflections are detected by a position sensitive photodiode, and it produces the corresponding topographic image of the surface. There are mainly three imaging modes. One is the contact mode, the non-contact mode, and the tapping mode. In the contact mode, we see that the tip is in contact and it is actually dragged across the surface. What happens here is, because of the strong attraction force, the tip just snaps into the surface and it damages both the tip as well as the sample. So this method is not preferred that much. Second is the non-contact mode. The cantilever used here is operated at a constant resonant frequency, and the van der Waals force of attraction tries to oppose this frequency. So this keeps it at a minimum distance, and which is also safe. The third mode, which is the tapping or the intermittent, also called the dynamic contact mode. As the name implies, dynamic contact which is in motion. So it is not in contact continuously, but it keeps oscillating and keeps touching at different places. So this lessens the damage to the surface, first because of the short duration of the applied force, and there is also lesser lower lateral forces between the tip and the surface. We can see many applications that we use atomic force microscopy for. First, we can determine the contact angle of droplets at a very minute scale. This is a small modification done, like using the tip, there's a small nanopore created, and the liquid we want to measure can be put through it. The tip acts as a pipette, and a single droplet can be obtained, and by the action of laser we can actually see the contact angle of different liquids. The next application is nanolithography. This is nothing but a technique where we can use AFM to draw high resolution structures that we need for high-end electron related applications. We can see that the figure is almost similar to the previous one. The only thing is that we specifically use a liquid for our required application. The process that takes place in nanolithography is that the liquid comes in contact with the surface. It starts flowing only at the point of contact, and this takes place mainly at the tapping mode, and the high resolution patterns which are created can give varied uses in nanotubes, nanowires, and protein nanoarrays, which are mainly used to detect the amount of proteins in blood samples. Another application we can use the nanolithography is, say we want to direct the electrons in a particular path. At some paths it's restricted and we want only electrons to flow in a particular path. That path can be the pattern which we make, and this is very much necessary in semiconductors to control the electron flow. I hope you understood what atomic force microscopy is, what is the components of the microscope, what is the principle on which it works, and the applications which are growing in today's world. Thank you.